Okay, so we are going to solve the problem 3.26 from Griffiths' book, third edition. So we have a three-dimensional vector space. And we are going to be using as basis, as our orthonormal basis, these vectors, the vector 1, the vector 2, and the vector 3. If you want, we can write this as these are three orthonormal vectors, right? So we can write them like this. This is 1, 0, 0. This is 0, 1, 0. And this is 0, 0, 1, right? Here we have three vectors. They are normalized. They are orthogonal, so they form an orthonormal basis. And we are given two states, which the book calls two kets. The ket alpha, the state alpha, is I. This is the probability amplitude I for the vector 1. Then we have 2 in the vector 2. And we have minus I for the vector 3. So following what we wrote above, we can say that this vector alpha is, as dimension 3, three-dimensional vector space. In the first element there we have the I. This I is the one for the vector, for the basis vector 1. Then we have this minus 2. So next term here is minus 2. And the last one is for that, according to that vector 3, so it's minus I. Okay? And we are given another vector beta, another ket, which is I for the basis vector 1. So this I is the probability amplitude. We have nothing in 2, but we have probability amplitude 2 in the vector 3. Okay, so again, we can write it as I, 0, and 2. All right, so this is what is given to us. And then comes first question. What is, so this is question A, construct the bra of alpha. Yeah? We are giving the ket, we want the bra of alpha. What is the bra? Is going to be the column. Instead of the column, is going to be a line, a row, and we have to do complex conjugate, right? That's the bra. So the first I that we have here becomes now minus I. Number 2 remains number 2. No, minus 2 remains minus 2. And this I here becomes plus I. Okay? So this is our bra. And for beta, again, complex conjugate. So we get minus I, 0, and 2. Okay, so writing just as I did is correct. If you want, you can write it like this. Minus I in terms of the basis vector 1, but now the bra. Minus 2 for the basis vector 2, and then plus I for the basis vector 3. Okay? And here, minus I for 1. For 2, there is nothing, is 0. So we go straight for the vector 3. Okay, so you choose how you prefer. I prefer this form, but if you prefer, you can write it like this. Both are good, okay? And I prefer this form. No? I find it easier to see, but you can also write it like this. And the solution manual prefers this form. Okay, so this is part A. Part B. Now, what we want to do So let me get some space here. Part B, what we want is the inner product, right, of alpha with beta. We have the bra for alpha, we have the cat for beta, so that's what we have to do. So that's why I like to write the vector in this form, as columns or lines, because then it becomes straightforward to compute this inner product, this um, uh, product between alpha and beta. What is the bra? For alpha is what we obtained above. So minus I minus 2 plus I. And what is beta was what was given to us. No? So I, 0, and 2. So here in one shot, we can get the answer, right? Minus I with plus I gives us plus 1. Minus 2 with 0 gives us 0. I with 2 plus 2I. Correct? So that's the answer. If you prefer to use the notation of the book, as we wrote above, the other option, I prefer it like this. I think it's very simple, straightforward to see. But if you prefer to use the other second notation there, you would go minus I with 1, minus 2 with 2, I with 3, and all that with respect to the beta. So the beta is I in the vector 1, then 0 plus 2 in the vector 3. And what we have to remember is these bases vectors, they are orthogonal, right? So this one with this gives us a number, but this one with that cancel because 1 and 3 is 0. Okay? Now, 1 with 1 is 1 because it's normalized. Okay, so if you go using this notation, I find this a little bit more tedious, but it's the same thing as we did above, okay? We're going minus I with I plus 1. Then the next, this one with 3, we said 0, so we don't look at it. Then we go, the vector 2, the bra 2 with 1, 0, because it's orthogonal. 2 with 3, 0, because it's orthogonal, so nothing from that. Then we go to the vector 3, the bra 3. 3 with 1, 0, because it's orthogonal. So we just go 3 with 3, and then we get plus 2i. So it's the same answer that we had above. So it's a preference of notation. I prefer, as I said, to write the column vector, and this line, I find it easier to see. Okay, so for the next question, which is to find this product between beta and alpha, I'll just do in that column form. So let's remember what the bra for beta was, minus I, 0, and 2. Okay, so here we go, minus I, 0, and 2. And the vector for alpha was I minus 2 and minus I. Correct? So that's what you have to solve. So minus I with I gives us 1. 0 with minus 2, 0. 2 with minus I, minus 2i. Okay? All right. So we got these results, and then comes the question. Confirm, now that we have these two, confirm that beta alpha is equal to the conjugate of alpha beta. Well, is this true? we just got above that this is 1 minus 2i. Okay. And the product with alpha and beta, we got here, 1 plus 2i, right? So this is 1 plus 2i, but we are looking at the conjugate. And you see that, yes, it's true. On the conjugate here on the left, 1 minus 2i. And on the right, the conjugate of that is 1 minus 2i. So confirmed. All right. So this is B. And then comes C. Is our last question. Now, they are asking us to find all elements of the operator A, big A. So we are given this operator big A, which is defined like this. Ket for alpha, bra for beta. Okay, so we have this operator. We want to find all elements, and then with these elements, we want to construct the matrix A. Okay, so to construct this matrix, it has to be a 3 by 3 matrix. No? So let me try to get some space here. This has to be a 3 by 3 matrix where this element here, the A11, let me write like this. Let me first put the element A11, A12, A13, A21, A22, A23, A31, A32, A33. That's the matrix that we want to build, okay? And we want to find what are the elements that we have to put there, each one of those elements. The element A11 means what? Is wherever the operator is in a sandwich with the vector 1 and 1. Okay, let me write one more. The 1, 2. This element 1, 2 is the operator that we have. No? So the operator A in a sandwich with 1, the vector 1, and the vector 2. So that's how we build each one of those elements. Once we have all of them, we can write our matrix. Okay, so let's pick some of them. The first one that we wrote there. Get some space, bring it. So this one that we have, what is it? Well, we have the basis vector 1. What is the operator? Is alpha and beta with 1. Now you have to remember what that alpha was, right? What the alpha and what the beta was. So I'm going to put it here. You have it above, but I'm going to write it again. This alpha, which was given to us, is I in 1, and then we have minus 2 with 2. We have a minus I with 3. You see that we don't care about what the component in 2 or the component in 3 because they are orthogonal with 1. So we actually only care about this one. Okay, so from this whole vector alpha with I, with 1, the only thing that will survive is this I. Okay, let's also write the bra for beta. So the bra for beta was minus I 1 and plus 2, 3. Yeah? So this was the bra. But again, what do we care about from this bra? Just the one, the component associated with 1, because 1 is normalized, but 1 with 3 we don't care about because the vector 1 and 3, they are orthogonal. Okay, so once we do this product here and this other one, what survives? The I and from this other guy, the minus I. So then we have the product, I with minus I, and this is then 1. Okay, so the first element that we are going to write here is just 1. Okay, let's try one more. Let's try the next one that we wrote, 1, 2, right? So we said this is 1 with the operator A and 2. 1 alpha beta, no? So this is the operator A and the vector 2. Okay, all right. So we have our alpha and beta written here. Well, so we already said that 1, this bra 1 with alpha, the only thing that survives is I. Okay, so I'm going to write it directly I. Now, beta, which is this, with this vector 2, well, there is no 2 here. 2 is orthogonal to 1, 2 is orthogonal to 3. There is no 2 here. And so the component for the vector 2 is 0, which means that here we have 0. So this element is 0. So there we go, 0. Okay? And that's how you go, one by one. Let's do just one more. 1, 3. The element 1, 3. So it's going to be 1 alpha, alpha beta with 3. Okay, so the first one we already said. 1, the only thing from the alpha that we can pick is that vector 1. So this amplitude I, that's what comes here. Now, beta, so this is beta. So this bra beta product with 3 gives us what? The only thing is the amplitude from 3 that can survive. Okay, so then we put here 2. And then you see that this is 2I. And that's what we're going to put here. And so you go one by one like that, and you will see that here we get 2I, here we get 0, minus 4, minus 1, 0, and minus 2I. And there is one last question. They are asking, oh, so is this matrix that we wrote here, this matrix A, is this matrix Hermitian? Okay, so the question is this matrix A Hermitian? A Hermitian matrix is a matrix so that the dagger is equal to itself. What is this dagger? This operation, when we are dealing with matrix, means you have to transpose the matrix. Okay, so you pick your matrix A, you transpose this matrix, and then you look for its conjugate. If this is equal to the original matrix, then it is Hermitian. Okay, so let me try to do this procedure here first. Okay, so I'm going to pick our matrix A, and I'm going to do the transpose of it. Okay, so the transpose means whatever is line becomes column. Okay, so my first line here, 1, 0, and 2I is going to become the first column. So 1, 0, and 2I. Second line, I just copied here. 2I, 0, and minus 4. And then the last line becomes our last column. So minus 1, 0, and minus 2I. Well, careful. Up to now, I only did the transpose of the matrix. Second step, we have to do the conjugate, no? So the star there. So when we do the conjugate of that, let's see. Well, whenever we have real numbers, nothing happens. But whenever there is I, we change the sign. No? So I'm changing the sign, changing the sign. So this is our Hermitian conjugate. Okay, so this is the Hermitian conjugate. So this is our a dagger. So this is the Hermitian conjugate. And our question is this equal or not to the original matrix A? So is this equal or not to 1, 0, 2i, 2i, 0, minus 4, minus 1, 0, minus 2i? Yeah. And the answer is no. No, it's not. So since they are not equal, we will say that no, it is not Hermitian. Okay, and that's the end of this problem.